So today we're going to talk about gradually varied flow modeling, and we'll spend the first couple minutes reviewing what we've done up to this point, or in the last lecture really, regarding gradually varied flow, and then we will get into how we model it. So we'll review gradually varied flow profiles, so water surface profiles. We'll introduce open channel hydraulic modeling of rivers. So hydraulic modeling could be a number of kinds of hydraulic models, right? We've done EPA net, that was hydraulic modeling of pipes. Of course, you could do modeling of pumps and a bunch of other things, so that's hydraulic modeling. Hydraulic modeling is also open channel. It's different software, different equations, right? But it's still hydraulic modeling. So I'm just going to specify that as open channel. And then we'll discuss applications for open channel hydraulic modeling. Here's just some examples of what we can do with hydraulic models. This is a two-dimensional, no, it's actually probably three-dimensional, computational fluid dynamics type of model. So this is the most complex, I think this is three-dimensional, it looks like it is, modeling. And this is showing different configurations of bridge abutments. So here's the fill that you would put into a river so that you would minimize the bridge span, right? It's cheaper and easier to put a bunch of dirt in, but you're constricting flow. So they're looking at how different types of abutments and ratios of river width to abutment or constriction width result in different kinds of hydraulics downstream. So here are flow lines that this model is tracking in 2 and probably 3 dimensions. And you can track where you would get scour, elevated velocities, or you might get deposition in these eddies downstream. So this is really cool and helpful because you can build this model relatively inexpensively and do a bunch of scenarios to figure out how our configurations of abutments are going to impact flow and sediment transport through this bridge span. Obviously, it's cheaper to do this than to build it and have it not work out, right? So the Journal of Hydraulic Engineering, ASCE, is a great journal for all this cool hydraulic modeling stuff. Got a couple articles in there if you want to check them out related to river restoration and flow metrics for that. So that's kind of for engineering applications, this is the big journal for that. For much more theoretical hydraulic applications, there's some more academic journals out there too. I wanted to show you all an example of some interesting hydraulics. This is the Great Sand Dunes. Has anyone been out there to look at this creek, Medano Creek? Let's take a look at it. So what are we seeing here? We're not at the ocean, right? Or it's a creek coming through the sand dunes. We're seeing these periodic waves passing through, or surges. Do you think the water is flowing at subcritical or supercritical conditions? So where I'm seeing kind of, you can imagine like standing out here with your foot, right? If you were to stop and splash, do you think a wave is going to go upstream? Certainly not when this surge is passing, right? But even in between, it doesn't look super intense, but this is probably supercritical flow or near critical flow because it's steep enough that it wouldn't propagate a wave upstream. So these surges are passing through every so many seconds, And it's just continual. What do you think's happening? Why are those surges? Why are they happening? Is it that we're getting pulses of water into the system? There's just something else going on. Right, is there some kind of inlet or outlet? So really this is just a natural system. There might be a ditch up there, but it's a national park, so maybe not. And that's happening on its own, and we'll look into a little bit why. So there's a paper out there, pretty old, from the 1990s. Gordon Grant's a fluvial geomorphologist with the Forest Service in Oregon. And he spent some time at the beach in Oregon. They have a lot of these streams and rivers that cut down through the mountains, the Cascades, and then enter the ocean there. And when they enter the ocean, they have to cross through dunes. And so he's out there on the beach watching these dunes kind of build up into little creeks and streams that are coming into the ocean. And maybe they start out flat, they start to develop. This is kind of an interaction between flow and the sand or the sediment. They start to develop ripples in the sands. Those ripples get really big, and then all of a sudden everything washes out, crashes, and goes back to flat conditions. And that's similar to what we're observing in Medano Creek, the Great Sand Dunes. So the flow is steep enough that we can gain supercritical flow conditions. That we're kind of moving and transporting sediments to create these kind of steeper conditions, at least across the backside of a dune. And then as that water accelerates, it's moving more sediment, it's starting to pick up and accentuate these dunes more dramatically. We start to get really supercritical flow conditions, waves, hydraulic jumps, and then everything washes out as this water accelerates and moves fast enough. And so that washout is then this kind of release of water. The bed becomes smoother, and then we get this surge of water that washes downstream. So it's actually a phenomenon that happens on its own through the interaction of flow and moving sediment and developing and moving that bed. So he went out and tracked the fluid number in these channels by measuring the discharge. So say the discharge was steady, you can measure then the velocity, and based on the cross section of the channel, and measuring the velocity maybe on different sides of the dune, the flow depth, and then calculate the fluid number. You saw that the fluid number was oscillating going above and below 1. So it's kind of hovering around critical. It's getting supercritical, subcritical, supercritical. And so it's always hovering around 1, oscillating back and forth as it goes through this cycle. So that's what's happening at Medano Creek too. And it's an interesting situation. Gordon Grant argues that a lot of rivers that are kind of steeper, that have mobile beds, will eventually create a slope, either through sinuosity or moving sediment longitudinally, will create a longitudinal profile slope such that it's oscillating between this fluid number of 1, critical flow depth, at a kind of channel forming type of discharge. This gets into geomorphology or the shape of rivers. But if we think of, for like a mountain snowmelt fed river, every year is going to get that kind of flood. It's going to change year to year. But that flood event is slowly moving and arranging sediments and establishing a width and a slope. And if it's a steep enough kind of system with a certain kind of sediment supply, he argues that this is going to be the condition that develops. That it's going to want to accelerate and create supercritical flow conditions, but it's not going to be able to maintain that for long because it's going to move the bed and create roughness, and then it's going to wash out and go back to subcritical. So this oscillation will occur on rivers. It's played out in some scenarios, but it's kind of cool to see in these sand systems. Just a little nature science for you. So last time we talked about these gradually varied flow profiles. We looked at mild slopes and steep slopes and transitions from one to the other. And the real kind of important thing to know is that a mild slope is dictated by the relationship between normal and critical depth, right? For a mild slope, our normal depth. And how do we calculate this normal depth? Where does that come from? How do we predict a normal depth given a discharge in channel geometry and slope? Well, the normal depth could be supercritical or subcritical. So for a mild slope, it's above critical flow depth. For a steep slope, it's below. To calculate the normal depth, we use Mannings equation. We assume that we have uniform flow conditions, and that's what the flow is ultimately trying to establish. If the slope and cross-sectional area were to be continuous into infinity, we would eventually establish the normal depth. So Mannings equation determines that. We can calculate the critical flow depth through the relations that we've talked about previously with specific energy. And we have a mild slope if, according to Mannings, our normal depth is above our critical depth. We have a steep slope if our normal depth is below the critical flow depth. So we could have supercritical normal depth. We could have subcritical normal depth. There's different kinds of gradually varied flow profiles. One of them that we talked about is the backwater. And this is where we have a mild slope that enters into a reservoir or some kind of ponding situation. And this is one of the examples that you'll do in this last homework assignment. So you'll actually plot a backwater profile. And this is what it looks like if you have a steep slope and you go into a backwater situation. You get a hydraulic jump and then it gradually merges with the elevation of the backwater. So based on what we've learned last time, I want you all to take a few minutes to draw what you think will happen for these different conditions. So in the first one, on the top one, we have a backwater. So it's a reservoir and it's going into a steep slope. So I want you to please label the normal depth and the critical depth on these lines. So if this is a steep slope, label where the control section is. And so that means what controls the flow depth, upstream or downstream. And then draw what the water surface profile is going to look like. And so in this case, we have a reservoir going to a steep slope. Here we have a mild slope going into a reservoir. And I have two different elevations. So I want you to draw out what could happen based on connecting with these two different elevations. So one would be a backwater, the other would be a little different. We're using the direct step method to calculate gradually varied flow profiles. This is a spreadsheet, and I've given you a video to walk you through it. But the idea is you're going to give it two different boundary conditions. One is a depth of 5 feet, and in this case, it creates a backwater. You have to figure out if you have a steep or mild slope, just given the discharge, and then that helps you determine where your boundary condition is. Is it upstream or downstream? So for a steep slope, your boundary condition is upstream, and you calculate moving down. For a mild slope, your boundary condition is downstream, and you calculate moving out. So I've set this plot up so that once you put the appropriate equations in here and plot everything, you'll get a nice plot that shows you the bed slope, critical depth, normal depth, and then your water surface profile. So why do we care about modeling the water surface profiles? We've been dealing with very controlled environments, a flume, a rectangular channel, maybe a trapezoidal channel with a constant slope. But when we want to track water and determine how fast and how deep it's going to flow at a given discharge, we're often dealing with systems that are much more complicated, like the Colorado River, which not only has a single main channel, but it has a floodplain. It's got side channels, right? Water can spill over levees that are surrounding these gravel pits at connected lakes, active gravel pits here. So real world systems are much more complicated. Even if we're looking at a canal, this is the Redlands Power Canal, where it comes out of the hydro plant. Even canals aren't straightforward, right? They may be in certain sections, but they're inevitably going to have curves and twists and changes in slope. And so if we want to figure out how to design a canal to convey a certain discharge, if we want to figure out how wide the floodplain is at a certain discharge, so we can build a bridge or determine where it might not be safe to have subdivisions or development, then we need hydraulic models to help us figure that out. So let's take a look at this video. All right, just a little bit. We actually spent a lot more time on this in hydrology, but we're talking about using hydraulic models to model floods and rivers, among other things. And so just a little quick talk about what floodplains are. We have a regulatory definition comprised of the floodway, which is this area that is really kind of sensitive, as well as the flood fringe. And the floodway is defined as the area that when you encroach up to the floodway, you can kind of push that water in and encroach it and confine it such that it'll raise up to 1 foot. It's kind of a weird definition, but it's really an area that no construction is allowed in. Sometimes construction is allowed in the flood fringe, but the floodway is fairly verboten when it comes to floodplain regulation. Does anyone know who manages floodplains and how that works? No, they don't. They manage water supply in some cases and reservoirs. It's actually a number of agencies. FEMA is one of the agencies that manages what's called the floodplain mapping and floodplain insurance programs. So a lot of federal dollars come to each state to support collection of LiDAR data. So high resolution topographic data, which we have from Mesa County, and actually most of Colorado at this point. They also help fund the hydrologic modeling. How much water can we expect at what frequency? And then the hydraulic modeling, which is where do we expect that water to be across a river and within a floodplain. And that's managed at the state level. So Colorado Water Conservation Board manages the floodplain program for Colorado. And then it's actually fairly voluntary. The floodplain maps are issued and adopted at the county level. They're regulated at the county level. And each county can kind of choose its level of participation. So it's a quasi-voluntary program, though the floodplain maps, if they exist, do have some regulatory power, especially when it comes to insurance. So if you're getting a mortgage and you're in a floodplain, you're typically going to be required to get insurance. So here's an example of a floodplain map. The red hatch area is the floodway. The blue outside of that is the floodplain outside the floodway. And this is all based on the 1% annual exceedance probability flood, or the flood that has a 1% chance each year of occurring. The orange is the 500-year flood, or the 0.2% annual chance flood. And in some cases, you can see it's a little more dramatic, but across the Colorado River in the Grand Valley, there's a pretty high bluff on a lot of these areas. And so there's going to be very little difference in the floodplain, the 100-year and the 500-year. That's going to change. If you're out in a more flat area, you're going to see a really big difference between those two floods. But where you have kind of high walls, there's not a big difference. So HEC-RAS, River Analysis System. RAS is the important component of that. HEC is the Hydrologic Engineering Center. They make a lot of different software out there. They make reservoir optimization software. They make hydrology software for predicting peak discharge and hydrographs. They do a lot, and RAS has been around. It's evolved. What we're seeing here is a series of cross sections that represent the river. So here's one of those cross sections. And this is just something that you might survey. When we look at LiDAR, and if you've taken my GIS class, you've dealt with that data, that's going to scan anything above the water, but typically you're not going to get any information from below. And so someone's going to have to get out there in the river and survey that either directly or from a boat. So it's often very involved to get the information that you need for a river model, a RAS model. Yeah, there is a type of LiDAR. It's called green LiDAR. So it just uses a different kind of laser. It is able to penetrate water to a certain depth. The water has to be pretty clear and not too deep. I think on the order of 2 meters at most. Any deeper and it stops, you start to get some pretty big errors. So it'll work for smaller rivers and streams, but not for bigger rivers. There's also some spectral techniques which will use imagery and evaluate the color of the water, and you're able to back calculate some rough depth estimates with that. And that's fairly sophisticated remote sensing type of analysis. That's mostly used in academia. It's not totally like out there in the practitioner world. So here's just some different views of what a one-dimensional HEC-RAS model looks like. I say one-dimensional because we're doing each calculation at a cross-section. So if I go back to this cross-section has an area, has a wetted perimeter. And anytime we run this model, we're going to calculate one value of average, discharge, velocity, and depth, elevation, right, for this cross-section. Of course, you can, for a given elevation of water, you can get different depths at this cross-section. So it's, there's some two-dimensional information there, but the calculation itself is a one-dimensional calculation. And so each cross-section basically just represents a point. There's one water surface elevation. And if you look at the profile, then you can see what the water surface elevation is for different flow rates. This might be a lower flow rate, a higher flow rate. And here is what that is in this kind of oblique view, where we're tying the water surface elevation into these cross-sections. And then these cross-sections also have X, Y, Z coordinates in space. It's a little hard to wrap your head around how this is one-dimensional, but there's a one-dimensional value here, and then we kind of extrapolate that into space, right? I'll show you some other examples of that when we do the walkthrough. So again, we use Mannings Equation. We use a gradually varied flow algorithm or numerical algorithm to calculate this. And depending if we're supercritical or subcritical, we give it a boundary condition. So if it's assuming a subcritical flow condition, then we say, okay, at downstream, for this discharge, here's the water surface elevation. Maybe that's something we measured. We could say, we assume that downstream is uniform flow, so we're just gonna use the Mannings equation to set the depth. So you have to tell the model where to start, and once you do that, it will calculate upstream and give you more information, or downstream if it's supercritical. So here's another example of a 1D model output, and it's confusing because this is a two-dimensional kind of flow depth thing. So this is showing depth of flow. The darker colors are deeper flow. This is just a made-up model for no thoroughfare canyon. Here's our LiDAR data shown as a hillshade image. And we put in a constant flow rate. And for a given cross-section denoted by these green lines, it calculates a flow depth for a certain discharge. So I put in like 5 different discharges, and it gave me a bunch of different flow depths. So if I take that flow depth as an elevation, And what RAS is able to do with their mapper function is stretch that elevation across the whole cross section and then interpolate from one cross section to the next. So if this elevation is 4730 and this elevation is 4727, then it's going to just linearly interpolate and then create a continuous water surface across that. And then also drape it across the landscape. And so it'll tell you, okay, if this is that elevation, then this is how deep it would be given the topography underneath. So still a one-dimensional result. You can do two-dimensional modeling. And two-dimensional modeling says that water can go anywhere from one cell to the next. So if one-dimensional modeling means that the water has to go from this cross-section to this cross-section, move downstream, right? One-dimensional modeling works perfectly fine for channelized flow that's going to stay in the channel and not necessarily split and go in a bunch of different directions. But if we have a situation where we expect the water to take many different routes across the floodplain to have more complex flow, then we can do a two-dimensional model. And this is where we're going to discretize the landscape or the topography into cells. And each cell can then have a flow depth, velocity, etc. And water can go in any direction that the equations determine it would go. With two-dimensional model output, we can track flow lines. So a flow line for a one-dimensional model would just be do, right? We only have one velocity, one flow depth, but in a two-dimensional model, each cell has a velocity and flow depth. And so we can track where flow disperses. This is flow coming through an estuary out into the ocean through a bridge. And you can see where we have really high velocities and how the flow disperses into the ocean. Here's a picture from that Mars model that our friend did. And again, you can see flow lines. So RAS has this visualization, which will show you kind of where stream particles will go. And the faster they're moving, the longer the tails are. And it also shows you the direction. So it's just a nice way to visualize where water's moving. And in this two-dimensional model that he made, you can see that it allows flow to split. So flow is going down this way, it's going around this way, it's going around this crater island, it's coming in around here. When we have complex flow paths, side channels, flow cutting across the floodplain, that's when two-dimensional modeling becomes important. Something about to blow? Oh, wow. Another example where two-dimensional modeling is important is on alluvial fans. Alluvial fans are very common in Colorado. If you look out at the book cliffs, pretty much every one of those drainages, you've got a valley coming out of the book cliffs, and then it hits the desert floor, and everything drops out of transport. So it creates this fan or this cone of sediment. And really, any valley that you're in, Colorado River is chock full of alluvial fans. When you've got a side valley coming in to a wider, flatter valley, a lot of the rocks and sediment that's kind of really steep that the canyons can transport down will not make it all the way to the river. And so it drops out in these fans that form over tens of thousands of years. In Boulder, there are a lot of fans coming out of the foothills. So here's North Boulder. The foothills are right here. And I think this is 4 Mile Canyon Creek or one of those in North Boulder. And what this shows is how when a flood comes out, it's initially channelized, but then it hits this fan area that also happens to coincide with really a lot of neighborhoods. And instead of staying in these channels, which you can see in green, the flow spreads out and is transported in the road network and all across Boulder. And this actually played out in 2013 when they had their big rainfall events. They were not expecting flow to go in the places that it did, and a lot of people's homes were flooded, at least unexpectedly, previous to that flood event. So fans distribute flow and spread it out because they're convex, or what is it? concave. I'm going to forget what that is. Anyway, they're shaped like this. So the flow is not going to just go down some channel. It's going to spread out, right? And that's where 2D modeling can be really important. So I told this story in hydrology, but one of my friends from grad school works for the company that made one of these maps for Boulder. And before the 2013 flood that they had, they did a 2D model. They did the hydrology, figured out what flow the 100-year flood would be, and showed the model to the city. And the city was like, get out of here. Like, this is out of control. Water is all over the place. This is bonkers. Go back to the drawing board. And you know, they kind of basically just said, we don't accept these results. Then the flood happened. And I'm sure I'm not telling this accurately, but I'm just going to roll with it. The flood happened. They went back and mapped where the water was from the flood events and overlaid it with the model results, and it matched up pretty well. So this is what happens when you have flooding on an alluvial fan. It doesn't stay in one particular channel. For HEC-RAS, you can have different model domains. You can have a one-dimensional model denoted as cross sections for the channel, for channelized flow, and then 2D model in the floodplain. So you've got some options to create different kinds of models in RAS. So next class, we'll take some time to do a walkthrough, and I'll show you just an example of a model for no thoroughfare canyon. And then if you have your laptops, we can work together on the tutorial that HEC-RAS has as part of it. So I'll send some instructions out for that for the next class.